For this worksheet, we have the three cars that are being pulled along by the engine. We see that we have a 3,000 kilogram car, 2,000 kilogram, and 1,000 kilogram. And then the first part right here asks what the free body diagram is going to look like and the equation for each one. Keep in mind that it says that the acceleration is 2 meters per second squared, which is going to be important later on. So for the first one here, for the 3,000 kilogram car, there's only one object that's pulling on it, and that is the second car. So that's a force. We're going to call that force 3, since that's the force acting on the third car. We also have a normal force and a force of gravity in the vertical direction, and they're going to be balancing each other. So to figure out what that force 3 is, then we're going to take that force 3 as the only force in the horizontal direction, times it, and that's going to be equal to its mass times acceleration. And we'll plug that 2 in later. For the second car here, the 3,000 kilogram car is pulling on the 2,000 kilogram, and the 2,000 pulling on the 3,000. So if there's a force 3 on the first car, then there's going to be a force 3 on the second car that's equal and opposite. So you can see the magnitudes of those are going to be relatively the same. So I try to keep in mind the vertical are balancing each other. So if you take the 3,000 multiplied by 9.8, about 10, then you get 30,000 for the vertical, and I try to make the proportions about equal. Since we're dealing with a grid here, then we can try to do that. You can see later on that it's not going to be very successful in doing that. So if the second car is being pulled forward, so we call that force 2, and that forward force has to be a little bit more than the backward force because it's still accelerating forward. So that force 2 minus force 3 is going to be equal to 2,000, the mass of that second car times acceleration. For the first car, the only forces pulling on are force 1, so that's the forward force, and then force 2 is pulling back on it. So those two forces are going to be equal and opposite. Now you can see that the force of gravity down is going to be a little bit less on this one because it's only 1,000 kilograms, so 1,000 times 9.8, and then a little bit bigger here, a little bit bigger here, because the mass gives you more mass with more force of gravity. So for this one, the horizontal direction, force 1 minus force 2 gives me 1,000 times acceleration. Now when we start looking at part B says, well, what if we include the 2,000 kilogram mass and the 3,000 kilogram mass as one system? Well, there's a couple of different ways of looking at it. Number one, you can look at it where you just draw a circle around these two, and the only outside force you really have is force 2. The normal force and force of gravity are going to increase. Since the scale was, it's kind of hard, so I just went beyond. It's not really to scale that well because there's not enough, basically not enough grid above or below. But we do know that those two are going to be equal to each other. The force 2 is going to be the only force left behind. Another way of looking at it is, since we're dealing with a 3,000 kilogram mass and the 2,000 kilogram mass, then if you took the force 3 then becomes an internal force because these two together have force 3 on the inside. But if you add these two free body diagrams together, since they're equal and opposite, they'll cancel out. That's why we don't put it here. For the next one, it says 2,000 and 1,000. So the 2,000 and 1,000, that's these two right here. So we got a force 3 pulling back and a force 1 pulling forward. So that's why we have it here. But if you look at the 2,000 here and the 1,000 here, you see force 2 is going to cancel because that's equal and opposite according to Newton's third law. So force 1 forward, force 3 backward, and we can see that the upward and downward forces, the normal force and the force of gravity, are going to be a little bit more because those two put together will give you those vertical forces. And then we get force 1 minus force 3. So force 1 minus force 3 is going to give me 3,000 because it's 1,000 and 2,000 together. The previous one was 5,000 because those are 2,000 and 3,000 together, and force 2 was the only force that was applying to it. And then the last one, if you include all three of them together, force 1 is going to be the only one. It got a ridiculously large up and down force because we're including all 6,000 kilograms. So then 6,000 times acceleration is going to be equal to that force 1. Looking over at the back, it says to figure out force 1, force 2, and force 3. So going back to the front, we can see that right here we can figure out what force 1 is. Here we can figure out what force 2 is, and then up here we can figure out what force 3 is. If you wanted to, if you figured out force 3, you could use this to figure out force 2, but those three are going to be useful as well, and really you can use any of them. You just have to do a little bit more math when you have to add another force in there. 2,000 or 2 times the acceleration again was 2 meters per second squared times 6,000. That gives me 12,000 newtons. For force 2, it was 5,000 times 2. That gives me 10,000. And then for force 3, that was 3,000 kilograms times 2. That gives me 6,000 newtons. And then the last one here, it asks about force 1, why force 1 is a greater force, 12,000 newtons, is greater than the 6,000 newtons, why it's more when it only pulls on the 1,000 kilogram car. Well, although it pulls on the 1,000 kilogram car, it's also pulling the rest of the masses behind it. So the force 1 is not only pulling that, but it's pulling all 3 cars. And because it's accelerating all 3 cars, then that means it has to have more force than just the force 3. Force 3 is only pulling on the 3,000 kilogram car, therefore there's less force that's required for it.